Okay, guys, I want you to recall the definition of linear transformation. We discussed in our last class that any transformation or mapping that satisfy these two conditions is said to be linear. And we saw one example in our last class. We'll continue this and let's look at example 4 and see whether this is linear or not. Just give me 1 second. I need to change the orientation of my computer. Okay, guys, all right. So TR to R, that means we are talking about real line. Okay, so let us consider two vectors in that. And C also is in R. Okay, so we consider A and B. Usually if it is R2, then we consider that as a vector, but in this case it is actually a scalar, right? Because you can consider this as a vector, but in either case this A, B and C all coming from R because it's going through, the domain is R. So we consider two vectors and one scalar from the domain. Keep that in mind. Two vector and one scalar from the domain. And what is given here is the given relation, given mapping is given T of x equals x squared. This is given. Now check the two conditions. Okay, we need to check two conditions. So condition number 1, T of sum of the vectors. So our vector is A and B here, A plus B. According to this definition, that will be, notice here, I replace x by A plus B. So I need to replace that x by A plus B also. A plus B squared. So that's going to give me A squared plus B squared plus 2AB. Right? And then let us calculate what is T of A. T of A means A squared. T of B means B squared. Just substitute the value. T of x is x squared. So T of A is A squared. T of B, you just substitute there. T of B will be B squared. So what we have noticed is T of A plus B is not equal to T of A plus T of B. They are not equal, you see. Because T of A plus B is A squared plus B squared plus 2AB, but T of A plus T of B is this, so they are not equal. So you don't have to check another condition. Okay, since condition 1 failed, T is not linear. Any question, guys? This is method 1. Method 2, you can do the same problem by, if you want to show that T is not linear, then you can just give one counter example. Okay. To show T is not linear, you can simply give a counterexample. That's another way of doing this. In order to show that T is linear, you must prove both of these conditions. But if you think that this is not a linear, then just give one counterexample. You can do this way too, but you can do in method 2, you know, by another method, alternative method. Let us suppose okay, so consider x equals to 2. Then we know that 1 plus 1 equals 2, we know. Everybody know that, right? We know this. Let's see what happens. T1 plus 1, which is actually 2. Now this is just like condition 1. A is 1, B is 1. You can suppose x equals to 3, x equal to 4, x equal to 10, doesn't matter. I just consider the easiest one. Okay, and I split that into two parts. If you suppose 3 and if you split that into 1 and 2, that's also fine. Nothing wrong with that. Okay, which means this is basically TF2, right? So that means 2 squared, which is 4. But TF1 plus 1, maybe you can do this way. TF1 plus 1 equals right, because TF1 plus 1, TF1 plus 1, you can write this 4 is not equal to TF1 is 1 and TF1 is 1. So 4 is not equal to 2. So this, you have already provided the counter example. Does that make sense? What we prove is that TF1 plus 1 is not equal to TF1 plus TF1. We have proved that because TF1 plus 1, which is TF2, that gives me 4, but TF1 is actually, you know, using that because the relation transformation given is this. This is the transformation given. So if you substitute that value there, you're going to get x squared. So here 4 not equal to this one, so T is not linear. So you can do either the method 1, method 2, doesn't matter. I want you to try this quickly, just for fun. I know you can do it, but let's try. Check those two conditions. This is given a transformation T from R2 to R2 such that T of x equals R of x. This is given. Okay, this one is a separate thing, okay? The question is just this one, given this one, so that T is a linear, R equals 0.5. Which means if R equal to 0.5, you can write this as R is 0.5 means 0.5x. Now we need to consider two vectors from the domains. So let us suppose that U and V belongs to R2. Okay, this is a two-dimensional figure and we consider these two vectors from the domain. Keep that in mind. So we always take these two vectors from the domain. from domain of T. Just keep that in mind. You don't need to write this down, but I'm just giving you, hint. And we consider one scalar, and let C be in R. C be a scalar. You can write C be a scalar or C is in R. So either language should work. Now verify the two condition or check two condition. Condition 1. T of u plus v equals, remember I replace that x by u plus v. T of x is, remember, 0.5x, so that's going to give me 0.5 u plus v. And T of u will be T of v will be, so T of u plus v is actually equal to T of u plus T of v. We have seen that, okay? So this one is, as you can see, this one is your T of u, this one is your T of v, because we found that here and here. So they are equal. So condition 1 checks. Now let's look at condition 2. T of Cu that's we need to verify. C is actually, this is given here 0.5. I replace that x by Cu, then I'm going to get 0.5. X means Cu. So I can write this as C 0.5u. Can I write that? Because this C is scalar and this 0.5 is also a scalar quantity. So scalar quantity are commutative all the time. So you can change the place, doesn't make any difference. Okay, because both are scalar. So that's going to give me, and T of u is, we already know T of u is, and we know T of u equals 0.5u. So what we can write is, so we can say that T of Cu, this equals this. So that means C, and this means actually T of u. So this condition also checks. Okay, since T satisfies both conditions, T is linear. Any question, guys, so far? Okay, now let's look at some properties. Okay, if we combine all the information that we have worked out with linear transformation, then we can conclude that if T is linear transformation, then T of 0 equals 0. That is one of the important properties. If T of equal to 0 If it is linear, then T of 0 must be 0. But if T of 0 equals 0 does not necessarily mean it is linear. So keep that in mind, okay? It's a one way. If T is linear, then this works. But if T of 0 equal to 0, can we say T is linear? T may be linear or not. Just keep that in mind. This kind of statement is confusing sometimes. And so if sometimes, to show whether T is linear or not, you just show that T of 0 is not equal to 0, then T is not linear. So that property will be really helpful. If this is the case, then we can say directly T is not linear. Another property is if you combine both property, the definition condition 1 and condition 2, you can write this: T of Cu plus dV equals C T of U d T of V for all scalars C and D and all vectors UV in the domain. So if I combine this, extend this, part B property, then I can write this. So if T is linear, then we can write this one. Just keep that in mind. Let's talk about identity matrix quickly. I think we discussed, you already know what is identity matrix, right? So identity matrix for I1 is 1. If it is 2 by 2 matrix, identity matrix is 1, 0, 0, 1. If it is 3 by 3 matrix, identity for that is this one. You all know, I think. Now, each of these columns of identity matrix are represented by E1, E2, E3. So they represent the column. So this means in this case, the first column is represented by E1, the second column will be E2, third column will be E3. In this case, E1, E2, and so on. Okay. Now notice one thing, that suppose I have X equals, let's say X1, X2, X3. Okay, there are, let's say this is a three-dimensional vector. Then interestingly, this can be written as X1, 1, 0, 0 plus X2, 0, 0, 0, 1, 0 plus X3, 0, 0, 1. Is that true, guys? Can I write that way? So because if you multiply this with this one, so you're going to get X1, 0, 0, 0. This will be 0, X2, 0. This will be 0, 0, X3. So if you add them all, you're going to get that. So what it means is we can write that as X1, E1 plus X2, E2 plus X3, E3. So any X can be written as this way. X can be written as this way. Just keep that in mind. Now let's look at a few examples here. So T is a transformation from R2 to R2 that maps E1 to Y1. What that means is given T of E1 is Y1, Okay, the transformation that maps E1 to Y1, and then the transformation maps E2 to Y2. This is given. And what is given here? And Y1 is given to be 4 and -3, and Y2 is given to be -2 and 5. Now part A, we need to find the image of x1, x2. Let's look at part A. Find image of x1 and x2. Okay, we know that x1 and x2 can be written as x1 E1 plus x2 E2. Everyone is okay with that? Can I write that way? Same logic as we have seen already here. So for the same logic, because x1 E1 means 1 0 plus x2 E2 means 0 1. If you add this, this will be x1 0 plus this will be 0 x1. So we can actually write down that x1 and x2. So this, we can write this one that way. So now given t is linear, so what we can write is we can write down t of x1 x2 equals t of, x1 x2 means x1 E1 plus x2 E2. We can write that way, which means because t is linear, we can write t x1 E1 plus t x2 E2. We can write that way. And because t is linear, then x1 and x2 are constant. So we can actually, using the second property, this is the first property, first condition of the linear from definition. And this, if you use the second condition of the definition, you can write x1 t E1 plus x2 t E2, which means x1 t E1 is already given. T E1 is y1. As you can see here, t E1 is y1 plus x2 y2. Now you can substitute the value. X1 means, y1 means, y1 is given, what is that? Y1 is 4n -3 plus x2, y2 is given, which is -2 and 5. All right, so in that case, what is this? Is this a vector equation or matrix equation?
Matrix.
It's actually a vector equation. Now we can actually write it down. I'm just checking this. This is 5x2. Can I write this way? That's it. Part A is done. So find the image. Okay. Now what it means is this t, what it does to x1 and x2 is it transform x1 and x2 into that. x1 transform into 4x1 minus 2x2, and then x2 transform into minus 3x1 and minus 5x2. In another word, t is a function that changes x1 and x2 into that. Okay, later we call this standard matrix. Okay, later what we do is in section 1.9, I just want to give you a heads up. So what we do is we consider the coefficient here 4, -2, -3, and -5, and then we call this standard matrix. We'll do that later. I'm just giving you a heads up. So in another word, this 4, -3, -2, 5, that's called a standard matrix. We'll talk about that later. Now let's look at part B. I'll do part B here. Part B, find the image of image of 1 and 2. So again, using the same technique, we know 1 and 2 can be written as 1 E1 plus 2 E2, right? We can write that way. Now, what is the image of 1 and 2? Let us use that transformation. So T 1 and 2 becomes T 1 E1 plus 2 E2. So since T is linear, because T is linear, we can write this down as 1 T of E1 plus 2 T of E2. We can write that way. Now substitute the value. Same idea as we did before. And substituting the value, what we know is 1 TE1, we know that that is Y1 because it is given there, and 2 Y2. So which means 1 Y1. What is Y1? Y1 is 4, -3, -2, okay, 4, -3 plus 2, and Y2 is -2 and 5. So your answer is going to be, how much is that? 4 plus 4 minus 4, is that 0? And that's going to be 10 minus, okay, 0 and 7. So this T, what it does is it transforms 1, 2 into 0 and 7. Any question, guys? Okay. Now, I think we are done with this section 1.8, but before we conclude this section, I would like you to try one question just for fun, okay? This example 7. Define this such that T, x1, x2, x3 is this way. Okay, guys, I want you to try this on your own. Given T of x1, x2, x3 equals x1 plus x3 absolute value, and so this is x3, and then this one is 2 plus 5x2. Question is T linear? That is my questions. Guys, can you try this? Whether you have definition of linear transformation at your disposal, okay, you can try using those two conditions, try to verify those two conditions, or you can use any one of the properties that we discuss. So the properties are here. You can use any one of these three properties. And also you can use the definition. So this one is coming from the definition, this one is coming also from the definition, and there is another extra thing. So you can choose to follow whether you want to provide a counterexample or you want to actually check both conditions from the definition. So it's up to you. You can do either ways. Is T linear? In this case, I noticed that the easiest method would be providing the counterexample, okay? So let me suppose that let us consider zero vectors. Okay, consider or let consider 0 vector in R3. Clearly this 0 is in R3, which means this means actually, this vector means 0, 0, 0. Just keep that in mind. Now I want to use this, condition 1. I mean the property, this property, 0 property. Okay, that's one method. So what I can write is, let us check what happens. T of 0, 0, 0, because if 0 is in R3, that means this 0 means actually 0, 0, 0. Just keep that in mind. This equals, I replace x1, x2, x3 all 0. So then that should give me, the function is given here, the mapping is given there. So I should be getting 0 plus 0, 2 plus 5 plus 0. What do I get? 0 and 2, which is not equal to 0, right? Which is not 0 vector in R2. You can write not 0, 0, or you can simply write not equal to 0. Okay? Since T of, maybe you can write this way here, T of 0 here. Since T of 0 is not equal to 0, T is not linear. This is method 1. Method 2, you can show that T fails one or both, one of the two conditions. T fails one of the two conditions of linear transformation. Definition. Okay, you can do that way. You can just try this second method just for fun by yourself. Any question, please let me know. Otherwise, we move to the next section now. So section 1.9 is about the matrix of a linear transformation, and the key concept are these two in this section. Okay, finding the standard matrix. Remember, we discussed quickly before standard matrix for a linear transformation. What is the standard matrix? Here is a theorem. If T Rn to Rm be a linear transformation, then there exists a unique matrix A such that Tfx equals Ax for all x in Rn. So it's very similar. You know, earlier we discussed one matrix. So that's what we will be doing. One of the key concept for this section. Okay. Here is the proof. So we have x equals, we know that x can be written as x1 e1, x2 e2, and xn en. We know that already from the previous discussion. Now tfx can be written as, okay, we replace that x here. X means this guy here. Tfx means this. So because t is linear, we can actually write down that as, you know, one by one, tx1 e1 and up to tx sub n en. And because t is linear, we can take that constant outside. So we're gonna get this. Now, what we got here is that, notice here, we got x1 t of e1 plus x2 t of e2 plus xn t of en. We got that. Now, this is a vector equation. So you can write that vector equation as a matrix equation. So if you want to write that matrix equation, so the matrix will be T E1 is your first column, second column will be this one, third column will be, and it goes like that, and the last nth column will be TEN, and then this will be, you know, x1, x2, x3 up to xn. So we can write this way. This is our matrix, which we call standard matrix. Let us represent that by A, and this one is actually our X. So we can prove that easily. So what we prove is T of X equals AX, and A is said to be standard matrix. So if it makes sense, great. If it doesn't make sense, just wait with one example. I think it will make things more clear. Okay, don't worry at the moment. Just keep that in mind that when we use that transformation with the vector, then you can express that as a matrix times the the vector, and that matrix is called a standard matrix. Now, before we discuss about this one, I would like you to take to high school just for a few minutes. And I want you to plot the points for me, please. In this case, my V1 is this, V2 is this, V3 is this. I want you to plot the point 1, 4. Okay, V1 is 1, 4. V2 is 3 and 2. And V3 is -2 and 1. So I want you to plot these points in the coordinate system, please. This is your X, this is your Y. And let us plot those points. So 1, 2, 3, 4. Or I can write this as ABC maybe. Let me write this as, okay, this one is V1, V2, V3, that's okay. Let me write this as, let's say A, B, C. Or you can simply write B1, B2, B3, doesn't matter. This is your B, no, C. Well, one point, 3 and 2, 1, 2, 3 and 2 right there, and then -2 and 1 right there. Okay, this one is, let's say, V1, V2, V3, or ABC, or PQR, doesn't matter. And I want you to join this line. We got a triangle, right? We got a triangle. Now, I want you to multiply this two matrix and write it down. What is the result? Multiply the matrix and please let me know what are the column of these matrix. Just multiply them. I'm waiting for your answer, guys.
It's 1, 3,
1, 3.
minus
-2,
Okay, thank you.
-4,
4,
-2, -1.
Okay, I want you to draw the points, these points. Now, the first point is draw 1 and, okay, so first point is 1 and -4. Second point will be 3 and -2. Okay, third point will be -2 and -1. I would like you to draw these points now. 1 and -4. I'll write this B1 prime. Another is 3 and -2. V2 prime. Another is -2 and -1. V3 prime. I want you to join this triangle. What is this? Recall from your high school. This is actually the reflection of the original triangle on x-axis, right? Okay, this triangle is just the mirror image of this over this. If the mirror is x, if the glass is x, so it's just like it's the image of that. So this guy is just looking at the image, image. So it's called reflection of the triangle over x-axis or on x-axis, maybe over x-axis then. Okay, notice that when we multiply a matrix by this one, 1, 0 and 0, -1, this will reflect the graph over the x-axis. And this has a very important applications in computer programming. A lot of time when they have the picture given, and what they do is they just multiply every point, every dot in the picture by this one, and they will reflect it over x-axis. Some of you, those who have done your computer programming, then you notice that, if you want to reflect some figure over some line, then that's what you're going to do in your programming, right? You use matrix a lot of time. In the same way, if I multiply this by -1, 0, 0, and 1, what is your guess? Does this reflect, or what does it do? Let's try that. Anyway, let's try part C first, and then we'll see what happens. Part C, instead of 1, 0, 0, 1, then what I did is 3, 0, 0, 3. Now I want you to multiply this. How much do you get? After this, we'll take a break. Okay, 1, -4, 3, -2. Okay, so 1. Oh, okay, so you did that. All right, so thank you, Khan. So I think you did this. But anyway, I'll leave that to you, but I want to focus now in part C. Part A and B are similar. We'll discuss that in a minute, but I want you to try this part C and let me know what is the multiplication of these two matrices.
So it's 3, 9, 3,
3, 9, 3.
9, 1, 1.
933.
9, 3, 3, 9, 3, 3.
Okay, all right. So what we notice here is that our A prime, this will be our vector, which is 3 and 9. This one is 9 and 3. This one is 3 and 3. Now let us draw the graph for this one and see what happened. And then we take a break. Okay, so first A is 1 and 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 6, 7, 8, 9. A is 1 and 3, which is right there. Another is, this is your A. B is 3 and 1, right there. C is 1 and 1, right there. So A, B, and C. So we got another triangle. Now let us draw this A prime. A prime is 3 and 9. So 1, 2, 3, and 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Somewhere here, this is my A prime. B prime is 9 and 3. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 and 3, right there. And this is my B prime. And C prime is 3 and 3. So 1, 2, 3, 1, 2, 3, right there. Right? What do you think? It's just a 3 times bigger than that, right? So because when we have this, then it actually, it enlarges the figure by a factor of 3. So this one is 3 times bigger than the previous one. Okay, so A prime, B prime, C prime is actually 3 times bigger than A, B, C. So 3 times the triangle. Triangle this equals that. I have actually a nice figure here. I have already drawn that for you. Oh, sorry guys, I made a mistake. It should be up, not negative.
Yeah, I was gonna tell you. I was about to tell you why it was down.
Everything is up. I was
Yeah,
checking
yeah.
if you are paying attention. 3 and 9.
So we are not doing it.
I have drawn here actually, so I don't want to do it again there. This one, this is, I think our A is, let me see, ABC. This is my A, this is my B, and this is my C. And now this is my A prime, this is my B prime, and this is my C prime. So what matrix does is, matrix actually is really helpful if you want to enlarge the figure in programming. Okay, if you want to make it smaller, if you want to make it, 10% bigger, 60% is smaller, you just write. If you want to make it 60% smaller for this triangle, let's say, then what you do is you just multiply these every points on that by the factor. 60% means you just do 0.6, 0, 0.6. Now, if you multiply the matrix coming from this triangle by this factor, then you are actually reducing the size to 60%. Okay, this will be really helpful. Okay, guys, let's take 10-minute break. Yeah, so now we will do a little bit of an experiment how the computer graphing works using matrix. First of all, please understand that there are different type of transformations. So, okay, even in linear transformation, we have seen that this one is reflection over x-axis here. and this one is reflection over y-axis. As we already know that each dot can be represented as a vector, right? So for example, this one is a vector represented by 1 and 3. You can consider that way. And every single point we can use the same coordinate, and so every single point represent a vector. So what happened here, if we multiply by this matrix 1 0 0 and -1, that's when we multiply, that will be reflection over this one. But when we multiply by -1 0 0 and 1, it reflects this one. Anyway, what I'm trying to say is that when we multiply by a matrix, then it will reflect, it will transfer, it will make some transformation. So here, reflection through the x-axis, we have seen this matrix. Reflection through y-axis, in this case x2, we represent that y by x2. This is the matrix. Reflection through the line, okay, through the line, reflection through the line, if you multiply that way, you'll get reflection through the line. And reflection through the line x equals -2 here, so that is the matrix, and so on. Now horizontal contraction, as you can see, if you multiply by this matrix, so k may have a different value. So if k is 1, it will not reflect, it will remain the same. If k is less than 1, okay, like 0.5 for example, then this will, what it does is actually it make a it will transform the figure, which is 50% less, as you can see here. If you multiply this way, it will contract vertically. If you multiply by this matrix, this figure looks like that. We call it shear transformation. Okay, there are two kinds of shear transformation. One is horizontal shear, another is vertical shear here. Okay, this, if you multiply this way, it becomes that. It just, tilted, it's slanting kind of thing. So we call it shear transformation, and so on. Now, let me just pull up one thing here. Can you see the picture of a fish there in your screen? Yes, okay, you can see the picture of a fish. Notice that every single point in the fish can be represented by a vector, okay? If I multiply all those vectors, using our hand, it takes a lot of time. That's why we take a help from the computer, because computer can do a lot of things, a lot of calculation really quickly. So what I did is I multiply this by the matrix, this one, 1 0 0 1. So what happens is that it will remain the same. It doesn't change anything. If I multiply by the one that we discussed earlier, 1 0 0 1, this fish will come down there. If I multiply by this matrix, it will reflect over the y-axis. Notice the matrix, I changed the matrix, okay? If I change the matrix, this one, this figure changes into that one, it transforms into that. It transforms with that by multiplying the matrix by this. And now I multiply by this, it just reflects through the origin. In the same way, let's see what happened, contraction here. Okay, if I multiply by this matrix for every vector on the first figure, it will remain the same. If I change the, you see, I change this factor to 0.8. See, it enlarges. Now this became the, you know, the fish on the right side is double of the size from the previous one, because I multiply that by a factor of 2 here. In the same way, if I do this, you know, it's now I change this y in E2, I make it E2 twice. So it will be the twice as large as the previous one. So if it is 1, it will remain the same. But if I go into decimal, you know, it just becomes smaller. That is the contraction transformation. Now let's look at shear. Here is a picture of a ship. Notice that when I change this, can you see what is changing here? And it gives us shear transformation. In the same way for vertical shear, as you can see, it's a vertical shear, and so on. Okay, once again, this has a really good applications in computer graphics. Okay. Now let me go back to my handout. Another transformation is rotating by an angle theta or phi. Let's look at this. Okay, give me 1 second. Now let us quickly review, before we start this, let us quickly review one concept from high school. I don't know whether we have covered that in high school or not. Do you know polar coordinate? You know polar coordinate? Let's say this point, I can represent that by x and y. What that means is, this is my x coordinate, this is my y coordinate, right? And that's why it is xy. Let us suppose that this angle is theta or phi. Or I can write theta. Let me write theta. Now from this figure, I would like you to tell me what is cos theta and what is sin theta from this triangle. Cos theta is, let's say this is r.
It's y over r.
Y over R, yeah.
And sin theta is?
X over r.
R.
So can I write this as y equals r cos theta and x equals r. No. Cos theta is x over r, isn't it? Cos theta is x over r, guys. So everyone is okay with that?
Yes.
Okay. Now I can write the same coordinate. I can represent it by a different, coordinate system. X can be written as r cos theta and y can be written as r sine theta. Okay. Suppose r equals 1. For r equals 1, what can I say? This point will be cos theta and sine theta. So the same point can be represented by this r cos theta and r sine theta in the polar coordinate and in a Cartesian coordinate. Okay, the simple regular, we sometimes call it rectangular coordinate system as well. It's simply x and y. Both represent exactly same point. So it's just a different way of representing the point. So when we revolve around some angle, then this polar coordinate will be really helpful to represent, okay, the coordinate. So we'll be using this r cos theta, r sine theta. But if r is 1, obviously this is cos theta and sine theta. Now, let's come back to this. Notice this one is my 1 and 0. And this is my 0 and 1. Suppose if this vector, okay, 1, 0, that is actually E1, remember, E1 is 1 and 0. That is my vector E1. This vector, if I rotate about phi, then I can write this as cos phi because this is x and y. We don't know what is x and y, but x and y can be written as cos phi and sin phi because the radius is 1. In this circle, the radius is 1. So we can write that way. Now, if I go phi angle on this side, by the same token, this will change into negative because x-axis will be negative on this side. So negative sin phi and cos phi. Does that make sense? Okay, anyway, so you need to know the little bit of a, trigonometry here. So this will change into sin phi and cos phi. So what happened is T E1, which means T E1 is 1 and 0. After the transformation, this becomes cos phi and sin phi, or sin theta for that matter. Okay, this will change. If we go theta, angle theta on that side, this will transform into that. And E2 transform this will transform into minus sin phi or sin theta and cos theta. Therefore, the standard matrix 1, 0, 0, 1 transform into this because 1, 0 transform into cos theta and sin theta, as you can see from here. And 0, 1 will transform into negative sin theta and cos theta, negative sin theta and cos theta. So this is now the formula for transforming which rotates by an angle theta. Okay, so let's look at some examples now. Example 1. Find the standard matrix for the linear transformation given by this. we want to find the standard matrix. Remember from the theorem, T of x equals AX, and then that A is called the standard matrix. Okay, so from theorem number, what is the theorem number again? You don't have to write that theorem, you can just simply write Tx, but just for the reference, theorem number, let me just go back. Theorem number 10. We can write that. So T of x means, now notice here there are 3 elements, means the domain is R3. So any point on R3 will be x1, x2, x3, we know that, we can write that way. Equals, what is given here is x1 minus 5x2 plus 4x3, and then another is x2 minus 6x3. This is given. Our goal is to write down this as in the form of AX. Okay, this is given. Can you write this in the form of matrix equation? A and X. What will be your A? Write down the coefficient 1, minus 5, and 4. X1 is 0. X2 is 1. X3 is minus 6. So this is in the form of A and X. So the standard matrix for T is 1 minus 5, 4, 0, 1 minus 6. So this is called a standard matrix. That's how we calculate. Any question, guys? So if you get confused here, maybe you can do this way too. Instead of, if you have a little bit of a difficulty going from here to there, I don't think you'll have, but if you have difficulty, then what you can do is you can first write down this as a matrix, I mean the vector equation, which will be x1, 1 and 0, plus x2, minus 5 and 1, plus x3, 4 and minus 6. You can go from here to there. I think it's not difficult. And then you just write down this, this, and this as a matrix here. Okay, but I trust that you can go from here to there directly. So in that case, you can skip this step. Let's try example 2. Example 2, it is given a standard matrix. The transformation is given. So given T of x equals 3x, it is given. What does this mean? And what is the domain? T is from where to where? R2 to R2. T is from R2 to R2. So that means anything in R2, the domain is actually R2, which means T of X means T of X1 and X2, right? Because any point, any X in R2 will be in that form, X1 and X2 equals 3X, you can replace that by X1 and X2. You're gonna get 3X1 and 3X2. Can you write that in matrix equation, guys? Let me know what is your standard matrix in this case. If you want, you can denote that by matrix A if you like. The standard matrix X for T is A equals this one. You can write that way. Now let's look at example 3. Do you have any questions so far? So our goal is to find the standard matrix for that given transformation. In example 3, we need to find the standard matrix of linear transformation R2 to R2, which rotates a point about the origin an angle of pi over 4 radian, counterclockwise. So let's look at that. I'll do it here, okay? Given T from R2 to R2. And it will rotate. Rotation is given as pi over 4. Is that right? Pi over 4? Yeah, pi over 4 radian. That is the rotation. So we know transformation by an angle theta is given by, standard matrix transformation by an angle theta. Okay, the language, let me rewrite this language. Our goal is to find the standard matrix. So standard matrix for the transformation is standard matrix for transformation or transformation by an angle theta is given by, we already know that, right? What is the formula that we derive? It is cos theta, sine theta, minus sine theta and cos theta. So cos theta, sine theta, minus sine theta and cos theta. So we already developed that formula. We can use that as a formula now. So, but theta is given pi over 4. So that's going to give me cos pi over 4 Can you please help me? What is the value here? Cos pi over 4 is?
Square root of 2 over, sorry, 1 over the square root of 2.
You are also absolutely right. Yeah, you can write this is square root 2 over 2, or you can write 1 over square root 2. It's the same thing though.
Okay.
Okay, and next one is, what is sine pi over 4?
Same minus 1 over root 2.
Okay, so this is your standard matrix. If you are given angle, then please remember this formula. Standard matrix formula. And then just substitute the value, not a big deal. Okay. So any questions so far? Example 4, I want to escape for the time.
Hmm?
Okay, guys, example 4, I want to take, I want to escape for the time being, because once we, we discuss about different kind of mapping, there are one mapping, onto mapping, and one to and then onto. Sometimes it's called surjective, bijective, and injective. So different kind of mappings are there. Once we discuss that, we will come back to solve this example 4. At this moment, maybe we want to skip that. Okay, section 1.9 is done. Chapter 1 is done. Now let me go all the way up to chapter 4 now. In chapter 1, you are supposed to do up to 1.9. Can you see handout 4.1, 4.2, 4.3, 4.4 in your screen now?
Yes.
All right, guys. Now we are talking about real vector space, vector and vector space. This is the main topic that we'll be talking today and in our remaining of the classes, okay? We'll be talking about vector space all the time from now. I want you to read this, whatever you can see in your screen, please read that first paragraph at least. Now you know what is space, right? The space is an area that is free to occupy, area or volume or whatever. And what is vector space? Well, an area that is free to occupy by vectors. But in mathematics, it has a very specific meaning. When we talk about vector space, it has a very specific meaning in mathematics. Here is the basic idea. A vector space is not just a space occupied by vectors. It is a mathematical structure formed by vectors and rules associated with it to handle these vectors. In other words, is reserved specifically for this mathematical use, for this use in math. Here is the definition. A vector space is a non-empty set V of objects. V is a set. It has lots of objects, and its objects are vectors on which are defined two operations called addition and multiplication by scalar. In this course, we normally use scalar as real numbers, but in the higher studies, then you can use that as, imaginary number as well, subject to the 10 axioms or rules listed below. In other words, vector space means it is a space, it is a mathematical structure whose objects satisfy all these 10 conditions. If you want to prove that the given space is a vector space, then you have to show that that space will satisfy all these 10 conditions. So I want you to please look at each of these axioms, each of these rules, conditions, okay? We have U and B vector from the space, and if you add these two, it must be within that space, whatever we call it, container, let's say. Okay, space is like a container, and we call it closure under addition. We have two vectors from that container, from that space, and if you change the position and add them, still they are equal. Associative property of addition. There is a zero vector in V such that U plus 0 equals U. We call it additive identity. If there is a vector U, then there must be another vector negative U in the same space, in the same container. Okay, if you have a container and you have U, then that container must contain minus U as well, so that when you add these two, you're going to get 0. We call it additive inverse. The scalar multiple of U by C, denoted by C. If you have U in the container, and then you have one number, C is a scalar, okay, number, and when you multiply that by this, then the product must be in the same container. We call it closure under scalar multiplication. And distributive, you have two vectors, and when you multiply sum of the two vectors, you multiply the scalar, then it must equal this. We call it distributive property of a scalar. distributive property of scalar from the left. And this one is this, we have two scalars d and one vector. U is a vector, and when you multiply, it should be equal to that one. It must satisfy that. In the same way, it satisfies that condition, and there must be a multiplicative identity. We call it 1. There must be 1. There must be a vector u. When you multiply that with 1, then you must get the same vector. So at the beginning, be a little bit confusing for many people. That's normal, but with some examples, I think you will be okay. Okay, using these axioms, we can show that 0 vector in axiom 4 is unique, and the vector negative u called the negative of u is also unique. That there can be, if there is, let's say, 0 vector in R2, then this 0 means 0. This 0 cannot be replaced by any other vector, so this is unique. In the same way, if there is u and negative u, and that is also unique. Now, very important thing to remember, if we want to show whether the given space is a vector or not, we're gonna follow this technique. Let me repeat that. In this section, our goal is to, they will, the questions will give us some space, some vectors, vector space. And we have to prove that the given space is a vector space. That is our goal in this section.
Sorry, your voice is not that clear.
Okay, just give me 1 second. Is this good?
Yes.
Okay, guys. Now, again, this section, some people find it really confusing at the beginning. I'll try my best to make it clear. Anyway, in this section, our goal is to, in the questions, given some spaces, and we have to prove that that is either a vector space or not. That is the goal. In order for that, these are the steps. These are the things that we keep in mind all the time. It is important to realize that a vector space consists of 4 entities, a set of vectors. Usually we take 3 vectors, 3 or 4 vectors, and then maybe few scalars, okay? A set of scalars, in this case, it will always be the set of real numbers R. Later on, this could be the set of complex numbers that in the higher studies. But for this course, all the scalar we consider are real. A vector addition denoted by plus sign and multiplication dot sign, okay? This one, addition and multiplication. But please remember, these addition and multiplication may have a different meaning. It depends on how it is defined. We call it binary operations, okay? Binary operations. Binary because there are 2 operations. Most of the time they have a usual meaning, but sometimes, it may have a different meaning. So we'll have 2 times 5 will be, 32. 2.5 will be 32. That's how we can define sometimes. Okay, so it depends. So the definition given to you. And scalar multiplication. Sometimes this symbol may have a different meaning as well. We need to keep that in mind. Now, we'll do this example 8, then we take a break. So that R2 is a vector space, meaning the space R2 satisfy all those 10 conditions. That's what we want to prove. Okay, always take couple of vectors. If I'm taking any vector in R2, then this will be U something like x1, x2, maybe U1, U2. This is one vector. V maybe V1 and V2. W maybe W1 and W2. Okay, usually we let this one be the vectors in R2. And we take couple of maybe two scalars, C and D are scalars. All right. What it means is R2 is a space. Okay, R2 means it is a space that we are familiar with. This is XY. This is R2. So in this space, we consider three general vectors and we consider two scalars. Now our goal, our job is to show that vectors together with the scalars satisfy all those 10 conditions that we discussed earlier. Okay, now we need to check 10 conditions. Some people might think that it will be kind of boring because, checking this for 10 conditions. At least at the beginning for one or two questions, we will look into all those 10 conditions. But after that, once we are quite familiar with this technique, then we will verify only 3 conditions. Okay, checking 10 conditions all the time is too much work. We'll prove one theorem that any vector space that satisfy 3 of those conditions will satisfy all the other automatically. Then we'll use 3, but at least for 1 or 2 questions, let us check all those 10 conditions. All right. Okay, I'm already warning you. Some find it boring, at least for checking those 10 conditions, but keep patience, and later on we will make life a little easy. Condition 1. Okay, look at the condition 1. So what we need to prove is U plus B must be in R. Let's check that. Okay, when I do U plus V, I get that. Do you think this one also lies in R2? This point? What I'm saying is, let's say I take, let's say 1 and 2, for example. This is your U, let's say, and your V is, let's say, 0 and 1, for example. If I add U plus V, then I'm gonna get 1 and 3. Do you think this also lies in R2 or R3 or R1? Where does that lie? Clearly in R2, right? So because it has 2 components. So if it has 3 components like 1, 3, 5, for example, it will lie in R3. But in this case, clearly this lies in R2. And this property is called closure under addition. Okay, what it means is when we take 2 vectors and we add the sum, we add them, then the result also lie on the same space. It doesn't go to R3, it doesn't go to R4, it doesn't go to R1. So now condition 2. So recall, condition 2 is, I believe it's a commutative property. So we need to prove
In condition 2, we need to prove u plus v equals v plus u. Let's check that. U plus v, we already got it. 1, which is u1 plus v1, u2 plus v2. And let's see v plus u. By the same manner, you can write this v1 means v1 v2 plus u1 u2, which is v1 plus u1 v2 plus u2. And we can write that as u1 plus v1 because these both are, like if it is 2 plus 3, 3 plus 2 are the same thing. So you can write that way, u2 plus v2. You can write that. So we have proved that u plus v equals v plus u. So this is checks. Okay, it checks. This also checks. This is called commutative property. Edison. Okay. In the same manner, we have to show how many conditions? 10, 8 more. Okay, guys, try this now. Now, condition 3. So the second property also checks. What we have shown is u plus v plus w. First, there was an association. There is a group of u and v. And we use the, Bodmas rule, or you can say PEMDAS rule, the order of operation. First, we need to work with u plus v because that is inside the parenthesis. We did that, but it turns out that this one and they are actually equal, so it checks. Condition 3 is done. Condition 4. Zero vector in R2 means, you can write this way. There is a zero vector. Zero means in R2 it will be 0 and 0. Vector in R2 such that, okay, what is condition 4 by the way? Let me go back, okay? Condition 4. There is a 0 in such that u plus 0 equals u, okay. Such that u plus 0 means u1, u2, plus 0 means 0, 0. equals, if you add them, you're gonna get u1 and u2. Okay, when we add 0 vector, then we got the same u vector. So this condition also checks. In other words, there is a 0 vector in R2. In the same way, keep on doing, guys. If you add them, what do you get is 0. We call this additive inverse. By the way, this property number 4, we call it additive identity. Six. Okay, what is condition 6? C for a scalar C. I think it's a multiply. Let me just go back. What is part C? Definition number 6. For a scalar multiple of u by c denoted by cu is in V. Okay, closure under scalar multiplication. For a scalar C, this is also in R2, right? Because there are 2 objects, 2 elements, so it must be in R2. It should not be in R3. It cannot be in R3. So yeah, if we multiply the vector by a scalar, then the result also lie in the same space in R2. So this is called closure under scalar multiplication. So this property is called closure under scalar multiplication. Okay. So similarly, I leave it to you. We can verify that. Verify the other, how many remaining now? Other 4 properties. Okay. I leave it to you. So property number 7 is you need to prove that Cu plus V equals Cu plus Cv. You'll prove that. And also you'll verify that C plus D both are scalar and you multiply with the vector, you're gonna get cu plus du. And then also you'll verify that c du equals c du. And then you'll verify the last one. If you multiply that 1 times u, then you're gonna get u. I leave it to you. Well, information, maybe you can check either your book or maybe in my lecture note. I'll leave it to you, okay? I trust that you can verify all of those the remaining 4 properties. So what is our answer now? Since the space, let me use a different color. Since V satisfies all 10 conditions, V is a vector space. Okay, done guys. Now you deserve 10-minute break. If you have any questions, let me know. Otherwise, we take a 10-minute break. Okay, in example 4, P sub n represent all sets of all polynomials of degree at most n. You know what is polynomial means, right? Suppose if you have a function, let's say polynomial of degree 3 means you have a plus bx plus cx squared plus dx cubed. So that is polynomial of degree 3. Polynomial of degree 2 means it will be a plus bx plus cx squared. That is polynomial of degree 2. Polynomial of degree 1 you can find in the same way, which is a plus bx power 1. Okay, I think you are familiar with this one. Now here Pn represents set of all polynomials of degree at most n, that is all polynomials of the form is a vector space. So we need to prove that this is a vector space. Instead of x in general, we use t as our variable, as our parameter, okay? Now, how do we prove whether it's a vector space or not? Well, we need to verify all those 10 conditions. But, you know, showing those 10 conditions every time, it's a lot of work, guys. So what we do is we will just verify 3 out of 10 conditions, namely condition 1, 4, and 6. And then later we will look one theorem. Okay, we'll discuss about one theorem. The theorem tells us that any space that satisfy condition 1, 4, and 6 automatically satisfy all the other conditions. We'll look into that later. But at the moment, we just verify those 3 conditions and say that if space satisfies these 3 conditions, then it is a vector space. That's what we're gonna do, okay? But if you want to verify all the remaining, all the 10 conditions, that's okay, nothing wrong with it. Now, in this case, let us consider at least 2 vectors, P and Q, let's say, or you can write U and V, doesn't matter. Let P and Q belongs to Pn. Okay, we consider 2 objects from that space. Pn is a container. Imagine this way: Ps is a container, and the objects, you know, this container has objects of this form. All the objects are in that form. Just keep that in mind. Where P is, I can write that P as a P of T. What kind of object is this? Is maybe A0 plus A1x plus A2 x square plus A3, not xt. You can suppose x, no issue there, but generally it is considered as t. Okay, so t square, A3t cube, and so on. It goes all the way up to an tn. This is your P, one object, and you have another object which, let us suppose that to be Q of t, which is maybe B0 plus B1t plus B2t square this is t raised to power n. So these are the objects, and let C be a scalar. So we assume two objects, two vectors from that container, from that space, and we consider one scalar. Now we verify all conditions, or you can say axioms. Okay. So first, condition 1. Condition 1 is we need to verify that it's closed under addition. Okay. Closure under addition is the first property. We'll verify that. Recall what it means is when we consider two vectors in that property we have seen, if we have two vectors u and v, if we add them, this also lies in the same space. That's what we need to prove. Let's look at that. P of t plus Q of t equals P is there in the space, in the container, Q is also in that space. So when we add them, so the sum will be in that space or not. That is our goal to check. Which means A0 plus A1t plus A2t square and tn plus B0 plus B1t B2t square B3t cube. Let's just write up to that plus B and tn. Now I can write this as A0 plus B0 constant term plus A1 plus B1. Let me take that t common plus A2 plus B2 t square an plus bn t to the power n. Can I write that? With little high school algebra, when we combine the term, we're gonna get that. Any questions so far, guys? Clearly, this is a polynomial of degree n, right? Because this one is a constant, a naught is constant, b naught is constant. When you add them, it's constant. A1 is constant, b1 is constant. Add them, you'll get another constant t, and so it is a polynomial of degree n. This means which means P of t plus Q of t also belongs to, this belongs to Pn. Okay, this is closed under addition. When you add two objects, then the sum of that also lies in the same space. Now, next, we'll look at scalar multiplication. That is, I think, property number something. Scalar multiplication. So that means what we do is C P of t also lies in the, let me write it down here. So our goal is to prove that this, when you multiply this polynomial P of t with the scalar c, then the product will lie in the same space Pn, P sub n, okay? So let's try this, what happens. C, P of t is actually a naught plus a1t Clearly, this is a polynomial of degree n. So it belongs to Pn. Okay, what we prove here is that when we multiply any objects from that space, from that container with some scalar, then the result also contain in the same space, same container. Okay, that's second property already proved. Now the third property we want to prove is the zero vector is there. Let's, I'm gonna go to the other side. Is there any question so far? I'll do it condition 3 here. Zero vector. Do you think zero lies in the space? Zero means, can we write this? Zero can be written as Is that true? 0 equals that one? Okay, great. So 0 also lies in Pn. Similarly, other properties can be verified easily. Hence, Pn is a vector space. All right, so from now onwards, we will just show these three, remember these three properties, and later we'll show that any space that satisfy those three conditions. First condition is closed under addition. Second is closed under scalar multiplication. Or you can write this as closed under scalar multiplication. Close under scalar multiplication. You can write that. And then the third one is zero vector. So any space that satisfies those three conditions will automatically satisfy all the remaining other conditions. Therefore, our goal is to just verify those three conditions, okay? But again, if you want, you can actually try all the other ones just for fun, but that's not required in the in proving the vector space. All right, guys. And we'll do one last questions. Do you have 3 minutes? I want to do one question now, which is example 2. Okay. So V is a container, okay, space whose elements, whose objects are from R2. It is from R2, but there is a restriction. If there is no restriction, then we already proved that R2 is a vector space. But when you impose some restriction that the X is non-negative and Y is non-negative, then is this a vector space? That's our question. Justify our answer. Here is a little hint. To show that it is not a vector space, you can just give one counterexample showing that one of the 10 conditions is not satisfied. So in order to show that this is not a vector space, just show that one of the 10 conditions is not satisfied by this space. That's it. So can you tell me whether it's a vector space or not? There are so many methods to do this actually. So one simple example is, let's say, let me randomly choose U equals, let's say 1 and 1. minus u equals I think that's pretty simple, right? The condition, which condition is that? Condition number 5. I think that is the easiest one. You suppose one vector, but if you look at the negative, so negative does not belong to, because this one is, you see, it doesn't belong into that V. So it is not a vector space. You can also prove another method. Maybe you can choose, you know, the scalar multiplication. It's not closed under scalar multiplication. So I leave it to you. Just look at, you know, this can be solved by so many methods. So try this, and if you want to, you know, if you want me to check your answers, then you can actually send me an email, or you can share your screen sometime in our next class. We are not able to finish this section 4.1. We'll continue this in our next class. And I think this must be today. We have just 3 minutes, so I don't have any other things to discuss. We're not able to do another, you know, another example because we only have 3 minutes. If you have any question, guys, let me know. Otherwise, this much for today, and I wish you have a wonderful remaining of the day, and see you on when? Thursday.